These are the my homework solutions rather, to the homework assigned, linear motion homework assigned in physics. So the assignment should look something like this. I gave you answers. I did a couple more examples on the back. I did a couple examples in class. So the goal is to try to understand how to solve these both graphically and with the equations that you were given. Hopefully you've got the equations 1, 2, 3, 4, 5 for linear motion on part of your formula sheet. They're organized, and you recognize that you may need to rearrange them to solve for something. So just as a disclaimer, I've solved things sometimes a couple of different ways. There are sometimes multiple ways to do this. The key is you've got to show me your work, and on a test you've got to circle your final answer so I know what you're doing. Otherwise I can't really award credit. So for the first one, which is PC 24, was windblown hair and can't swim ashore or sailboating, and they start from rest. They have a uniform acceleration of 0.29 meters per second squared for 18 seconds. You want to find out how far they traveled. So I wrote down the given information here. I tend to like to do that in one spot. So this seemed to me to be a version of Formula 4, which would work. So 1/2 AT squared, there is no initial velocity, so that would basically, that whole term would become 0. So 1/2, 0.29, 18 seconds squared, comes up to 47 meters. Okay. For problem 2, there are a few parts to that. It was a funny car competition. So interestingly enough, someone named John Forrest did this, and they completed the quarter-mile dragster race in 4.437 seconds, determined the average velocity, then the average acceleration, and the final velocity of the car. So the average velocity is Formula 1. That's change in position over change in time. It told us that 1 mile was 1,609 meters, so a quarter mile is 402.25. So I just simply take that, and I got 90.6 meters per second as my average velocity. Now for part B, and this is supposed to be a B over here, it's asking you to find the acceleration. You need to be a bit careful about that. So you could use this formula, but the problem is if you just put 90.6 in for this, your answer is going to be wrong. It'll actually be half as much as it should be, because this delta V means a change in velocity. So that's final minus initial. This is average. So you could use formula number 2, which we don't use very often, and realize that if the average is 90.6 and the initial is 0, the final velocity would actually be about 181 meters per second. If you put 181 divided by 4.437, you'll get the correct answer. So I use this again, which is similar to what I did in number 1, or the first problem. And in this case, I know the displacement is 402.25. I know 1/2 A, just what I'm trying to find out, and it's 4.437 squared. So I end up with 402.25 equals 9.84 times A. Get A all by itself, it's around 41 meters per second squared. And then now, for C, I can figure out the final velocity. So 0 initial meters per second, 40.9 times 4.437. Again, you could have done this a different way using Formula 2. For PC 13, I asked you to use the graph. You could use in equations, but I want you to be able to use both, and you'll need to use both on your test. So in this case, the acceleration is the slope of a velocity time graph. So that's change in y over change in x, so that's change in velocity over change in time in this case. So I have finished with 0 meters per second. I start with 18, so 0 minus 18. I finish at 6 seconds. I start at 0 seconds, so that's 6 minus 0. So that's negative 3 meters per second squared. So hopefully, if you see a graph like this, you would know that that's a negative acceleration. For part B, you should understand that the area of a velocity time graph is equal to the displacement, and in this case, that's actually the same thing as the distance traveled, because we're only going in one direction. So 1/2 height times base, or base times height, 1/2 times 6 times 18 gives me 54 meters. For PC 18 here, this is asking about a small plane taking off at 28 meters per second and determining the minimum length of the runway if it accelerates at 1.9 meters per second squared. So in this particular case, I know the initial velocity is 0 because a plane starts from rest. I know the acceleration. This VF is actually a final velocity. It's the takeoff speed. So I want to find the minimum length of the runway. I don't know time. Now there's ways I could do that. I could use time is equal to change in velocity over acceleration and find time, and then plug that into another formula. Or I could just use this formula, which is formula number 5. Final velocity squared equals initial velocity squared plus 2 times acceleration times that change in position, or that length. So that's what I did. So I got 28 squared equals 0 squared plus 2 times 1.9 times delta x. So 784 equals 3.8 delta x. That comes out to 206 meters. That's very short. That's about, 650, 700 feet. But for a very small plane, that's reasonable. For a large plane, like a jet airliner, you'd take about 5,000 feet. For PC-20, Susie loves to ski, or Lavatsky, loves to ski, I don't know, has reached the end of a ski slope and slows from 29 meters per second to 1.8 meters per second in 1.45 seconds. So you want to determine her acceleration and the distance she moved. So acceleration is going to be found with equation number 3. Final minus initial over time. Again, this should be a negative value because she's slowing down. Here, once I have that acceleration, I can plug that into a version of formula number 4. I need to use the full version because I'm not starting from rest. I'm not starting from 0. So it's a positive 29 times 1.45 seconds plus 1/2 negative 18.8 times time squared. Notice that although the units for acceleration are meters per second squared, I don't square the value. So that ends up being about a positive 22.3 meters. For PC-28, I've got an initial velocity of 10.4 meters per second. That may not seem great because you're like, wait a minute, it has a terminal speed of 10.4 meters per second. Well, that's where he drops, the speed at which he drops the camera. And so that's actually the initial speed of the drop camera. So he's dropping it from a height of 52.1 meters. You should know at this point that gravity accelerates things vertically at 9.8 meters per second downward. That was in the first page of the notes. So to find the final velocity, I could try this, but the problem is I don't know this time. So again, I don't think I can use this formula. That's okay. I'll find another way. In this case, I'm going to use formula 5, VF squared equals VI squared plus 2A. I'm calling this delta Y because it's vertical. It doesn't matter if you call it delta X. It's just a change in position. So VF squared is equal to 10.4 squared plus 2 times 9.8 times 52.1. I get VF squared is around 108, so I take the square root of that. Oh, plus 1,021. So that ends up being 1,129. Square root of 1,129 is around 33.6 meters per second. So hopefully it makes sense that the object will speed up if gravity's pulling down on it. And it went from 10.4 meters per second up to 33.6 meters per second. So now, when I want to find out how much time it took to fall, I'm going to use a version of formula 3. This acceleration is equal to change in velocity over change in time, but I'm going to rearrange that to solve for delta t. So I'm saying delta t is equal to change in velocity over acceleration. So it sped up by about 23.2 meters per second, divided by 9.8 meters per second, and that's around 2.37 seconds. Number 30 is the last one that's from the physics classroom. And it basically is something that's in free fall. You've got an object. It can fall 132 meters. Its initial velocity is 0. Its acceleration is 9.8. And so it's asking how much time it takes. I use a version of formula number 4. I use delta y instead of delta x again because it's falling vertically. That's the y direction. I don't care if you say delta x or not. And so there is no initial velocity, so it's just the version 1/2 at squared. So 132 equals 1/2 times 9.8, which is 4.9 times t squared. So I'm going to divide 4.9 on both sides of the equation. That becomes 26.9 equals t squared. So t is around 5.2 seconds. For part B, it's asking you to find the final speed of the object before the braking period begins. So if I start at rest, that's 0 meters per second, my final velocity is equal to acceleration times time. So that's around 51-ish meters per second. Number 8, I can talk about if you want to in class, but the key here is there's symmetry to this problem. So we are going to have a unit on projectiles, which deal with things that have both an acceleration in one dimension and a constant velocity in another dimension. This is the simple version of it, where something's going straight up and straight down. The key here is the symmetry of the problem. The time up would equal the time down, and that's half the total time. So if you're given a time of 3.56 seconds, half the total is 1.78 seconds. You also should realize that at the top of the path, the object's not moving up or down, so it's 0 meters per second velocity, and acceleration always acts down at 9.8 meters per second per second. So this is easier if you think about the first half or the second half of the problem. I tend to choose the second half of the problem because it means that my gravity is acting downward, and I can treat that as positive. And I can treat my velocity as positive downward. So I don't have any negatives to deal with. And also I have an initial velocity of 0. So that means I can use a simple version of this formula number 4. Delta y, again, if you want to use delta x, that's fine, was 1/2 a t squared. And notice I'm using half the total time because it's only falling for 1.78 seconds. So when I do that, I get 15.5 meters. If you figure this out but used the entire time, you would have gotten 4 times as much, or somewhere around 62-ish meters. For part B, if I'm looking at the velocity of the throw, that should actually equal the final velocity of the object just as before it hits the ground. So again, I could think about the velocity on the way up or on the way down. It would be the same amount. So I probably would choose the second half of the problem because I did know this height now. Oops. So I guess I could use this. And this one's unknown. So I think I could use this. The tough part is the initial velocity is up and acceleration's down. So that means I'd have to be careful about putting this as a positive, this as a negative. If I think about it on the way down, I can think about something like this, where my acceleration is equal to change in velocity over change in time. So I know that my initial velocity on the way down is 0. I know the time on the way down is 1.78. I know acceleration is 9.8. So I figured it out that way. So that's a little bit more of a complicated problem, but again, it deals with thinking about writing down what you know and then simplifying something complicated by looking at the pieces parts of it. Hopefully this helps.